We are now in the easy part of B. Previously, we just showed how to figure out an upper bound for the Rowan probability on a finite time horizon 0 to delta U. Now, this upper bound is an upper bound for all alphas that are non-positive and which satisfy that the cumulant generating function evaluated in that alpha is non-negative. So this can be one number for one alpha and another number for another alpha. The thing we want to do now is to find the strictest bound possible by choosing a correct alpha. So the thing we want to do is we want to find the smallest possible value of this bound here. And that is what we're asked to do here when they say show that the Rowan probability is smaller than equal to e to the minus u and then some special g delta where g delta looks funny in some special way. So what we're going to do is we're going to find the infimum of e to the minus u g delta of alpha, where we consider all the alphas that make sense to consider. And according to the exercise, we're asked to consider those alphas smaller than or equal to 0, which make our cumulant generating function non-negative. So we're going to try and find this value, and this value will then be greater than or equal to our Rowan probability, because we know that the infimum of this thing here is also the smallest, well, it's the greatest number that is smaller than this for all alpha, and it is also greater than or equal to the Rowan probability thanks to the strict inequality we have here. So in order to find the strictest bound, all we need to do is to find the infimum of this expression. Now, before we can continue, what we need to look at now is the set of alphas that we minimize over, because we're considering those alphas smaller than or equal to 0 that allow for the cumulant generating function to be greater than or equal to 0. Now, how does a cumulant generating function look? I think that this has been a part of the lectures. During lectures, you've learned that the cumulant generating function is convex. That means it behaves like a smiley face and goes through 0, 0. So what that means is it goes through 0, 0, and as long as the adjustment coefficient is well defined, it also means that at the point where it goes through minus r, then before it crosses minus r, the cumulant generating function is positive, and after it crosses minus r, it stays negative until it goes through 0, 0. So that means that the only alphas that are negative for which the cumulant generating function is positive are those alphas that come before minus r. And therefore, finding the infimum of e to the minus u g delta alpha is exactly the same as finding so finding the infimum over this set is exactly the same as finding the infimum over the set of alphas that are smaller than or equal to minus r. And now we continue. So we want to find the infimum of this expression. Well, that's just the same as saying, well, how do we make this expression as small as possible? Well, by making this thing here as numerically large as possible. So this is equal to e to the minus u, and then by trying to make this thing here, not as numerically, but just as large as possible. So we will try to find the supremum of g delta of alpha over those alphas that are smaller than or equal to minus r. And this is exactly what we wanted to find, the e to the minus u g bar delta that was asked of us in the exercise. So we have found that the greatest number that is smaller than this value for all the alphas that make sense to look at is given by this. And since we have a strict inequality, we have that the strictest boundary we can find for the ruin probability on a finite time horizon is given by e to the minus u g bar delta. Okay, so that was B. Now, look, the funny thing here is in the entirety of B, we have actually not used the fact that the increments are assumed to be normally distributed. So any type of random walk suffices to yield the results that we have in B, as long as the cumulant generating function behaves in such a way such that the adjustment coefficient is well defined. And that's actually quite nice. It might be confusing for people who think that they should use A to solve B, because this is actually one of the cases where B can be done just as a standalone. In C, we're going to have to apply the cumulant generating function in this specific case in order to look at a couple of things, but we'll take that when that comes.